You know that feeling, right? That clammy, sweaty wristband just clinging to your skin after a good workout, maybe leaving that little red mark.
Oh, yeah. Or worse, the rash.
Exactly. Or maybe it's that little nagging worry in the back of your mind. Is that camera really off? Are my most private workout moments being captured somewhere?
It's a real concern for a lot of people.
It is. We've all kind of wrestled with these trade-offs with modern fitness tech, haven't we? You want the accurate data, sure, but it clashes with the discomfort or the privacy worries or just the frustration when a gadget doesn't quite get your specific moves right.
Hmm.
Well, get ready, because today we're taking a deep dive into something that promises, well, to solve exactly those dilemmas.
This sounds interesting.
It really is. We're going to unpack an incredible new piece of research introducing something called tinyRadar. It's a novel, on-edge millimeter wave radar-based fitness tracker.
Okay, millimeter wave radar. So, not cameras, not wearables.
Right. And this isn't just like a minor upgrade. It feels like a fundamental rethinking of how we interact with tech for personal well-being. Genuinely cutting-edge stuff, pushing boundaries by putting you and your privacy first.
That's a refreshing angle.
Isn't it? So our mission today is pretty simple. We're here to cut through the technical jargon, hopefully, bring you the surprising facts, and just give you a real shortcut to being truly well-informed about this innovation.
Good goal.
You'll understand the problems tinyRadar is cleverly solving, how it actually works its magic. And it does feel a bit like magic, and why it represents such a significant leap forward in personal wellness tech.
And, if we look at the bigger picture here, this really is about much more than just, say, counting reps in your living room.
Right.
It's potentially about a paradigm shift in how we approach personal well-being technology, really prioritizing both efficacy in tracking and an unwavering respect for your privacy.
Designing tech that serves you without constant compromise. I like that.
Exactly. That's the ideal.
So what's our journey for this deep dive going to look like? We'll kick things off by exploring those common frustrations, the ones we all feel with current fitness tech.
The pain points.
The pain points, exactly. Then we'll unveil tinyRadar, diving into its core concept and the clever hardware that makes it all possible.
Okay.
After that, we'll pull back the curtain on how this device actually sees and understands your movements, literally turning invisible radio waves into a precise map of your activity. It's pretty cool.
That's the core tech. Looking forward to that.
Yeah. Then we'll explore the powerful intelligence that's built right into the device itself, the tinyML, that allows it to recognize exercises and count reps with, frankly, remarkable accuracy.
Ah, the tiny machine learning aspect. Crucial for edge devices.
Precisely. And finally, we'll examine tinyRadar's real-world performance, what it can do right now, its current capabilities, and maybe gaze into the crystal ball a bit. Look at the expansive future possibilities this tech opens up. Everything from enhancing personal fitness, maybe, to revolutionizing elder care.
Big potential then.
Huge. Okay, let's get into it. All right, let's start with something I think many of us know all too well. The wearable woes.
The wristband itch.
The wristband itch. Who hasn't felt that discomfort? The tight, sweaty wearable after a long workout, or maybe even just wearing it all day on a hot day.
Right. That constant pressure, maybe moisture trapped underneath. It's not pleasant.
It's really not. And it's not just about comfort, is it?
Yeah.
It can actually lead to skin irritation, rashes, sometimes even mild allergic reactions for some people.
Definitely. And you have to remember, these devices are often designed for round-the-clock monitoring, right? So that means prolonged skin contact day in, day out.
Yeah. And sources we looked at highlight just how common discomfort, irritation, even things like allergic contact dermatitis can be from these devices.
Yeah.
It's a significant barrier.
It absolutely is. Even for dedicated fitness folks, it can stop you from using it consistently. You want to focus on your workout, not an itchy wristband.
Or that weird tan line it leaves behind.
Yes, that too.
But beyond just the physical discomfort, another frustration often creeps in, doesn't it? Accuracy.
Ah, yes. The accuracy question.
Have you ever felt like your wearable just wasn't quite getting your workout? Maybe you're doing something dynamic, a full-body exercise, but your device, stuck way out on your wrist, only seems to capture a tiny fraction of that movement.
Yeah, that happens. Like, if you're doing lunges or burpees,
Yeah,
a wrist tracker might completely miss what your legs or your core are actually doing.
exactly. It can give you false or just totally incomplete results. And some of the research points this out. Wearables attached to just one part of the body, they can struggle because they fail to capture the entire movement, especially when other limbs are really active.
And then there's the sweat factor.
Oh, the sweat factor. The kicker is a little sweat during exercise, which is, kind of the whole point, can sometimes cause the device to lose proper skin contact.
Right, it slips, or the sensors just can't read properly through the moisture.
And that throws its sensors off entirely, leading to inaccurate data. One source mentioned this specifically. So not only are they sometimes uncomfortable, but their very ability to track your effort can be compromised by the activity itself.
It's like they give up just when you start working hard. It's counterintuitive.
It really is. It feels like you're fighting the technology sometimes.
And this leads us to another critical point, perhaps the most concerning for many. While the convenience is great, what's the true cost when it comes to your personal information?
The privacy angle.
Exactly. We're talking about generally three main categories of data these devices love to collect. First, there's what we call personal data, or PD. That's stuff like your name, age, gender, usually given during setup.
The basics.
The basics. Second, activity data, AD. That covers all those health metrics. Step counts, calories burned, heart rate, sleep patterns, you name it.
The stuff you actually want to track.
Right. And third, maybe the most sensitive, is geolocation data, GD. That's pinpointing your mobile device's precise location, where you are, where you've been.
Okay, so PD, AD, GD. Got it.
The problem, as several sources we looked at highlight, is that modern wearable trackers are just incredibly susceptible to privacy violations precisely because they collect all this sensitive data.
How so?
While vendors might gain ownership of this data through vague terms of service, they might even collect more information than you're explicitly aware of.
That's sneaky.
And what's even more concerning is where it goes. This information can be stored on a cloud server, potentially vulnerable to breaches, or even sold off to third-party vendors.
Sold. My step count.
Your step count, your heart rate patterns, your location history.
Yes.
That seemingly innocuous fitness data can become a commodity. It potentially exposes you to unforeseen privacy risks down the line.
Wow. Okay, that's definitely something to think about. Your digital footprint getting bigger without you even realizing it.
It's a very real concern. Now, if we shift gears slightly and look at camera-based trackers, well, the privacy concerns become immediately apparent, and frankly, much more acute.
Yeah, I can see that coming.
While these systems can offer rich visual data by monitoring your movements, the whole idea of video surveillance in your most personal spaces, your living room, your home gym, it's just a non-starter for most people.
Totally. One source flat out stated that camera-based fitness trackers generally pose significant privacy risks. It's pretty obvious why.
Very few of us are truly comfortable with a camera recording our workouts, even if it's supposedly just for personal use or AI analysis. It feels way too invasive.
So we're presented with this tricky situation, aren't we? It feels like we're trading one set of problems for another. Cameras might track whole body movement better, maybe giving better accuracy for complex exercises.
Potentially, yes.
But at what cost? Not just to our privacy, but surprisingly, also in terms of the sheer computing power needed.
That's a key point. Some methods try to get around the privacy issue by, say, blurring faces or obscuring identities algorithmically.
Right, I've seen that mentioned.
But doing that requires complex algorithms. It adds significant computational overhead. These systems often end up needing extra hardware, like a dedicated PC humming away in the corner, or a constant high-bandwidth connection to a cloud server for processing.
Which kind of defeats the purpose of a simple home setup, right? It limits portability, scalability.
Exactly. And there's another practical snag. Forget about working out in low light or maybe even slightly foggy conditions if you're in a garage gym or something.
Oh, right. Cameras need light.
Camera-based systems can fail to function effectively in those situations, as one source detailed. So it feels like we're constantly hitting these walls with the existing technologies.
Yeah, whether it's discomfort, inaccuracy, or that really deep personal issue of privacy, it seems like there's always a compromise.
What I find particularly clever about tinyRadar's approach is how it navigates this specific trade-off you just mentioned. With cameras, to protect privacy, you inevitably add complexity and computational burden.
Right, the blurring algorithms and so on.
Exactly. This additional processing demands more powerful hardware, external PCs, cloud servers. It completely undermines the idea of a simple, portable, easily scalable solution for personal use.
It pushes the processing away from you.
Precisely. It often centralizes it, which then, ironically, can reintroduce potential privacy and security vulnerabilities that you were trying to avoid in the first
Ah,
place.
good point.
And the limitations in low light conditions just underscore that these camera-based systems are far from ideal for a truly, ubiquitous home fitness solution. tinyRadar seems to fundamentally shift this paradigm.
Okay, I'm intrigued. Let's get into it.
Ooh.
Okay, let's talk about what feels like a genuine game changer here. Imagine a device. It tracks your fitness, but it never touches you. There's no camera watching you. And it doesn't compromise your privacy,
That sounds like the holy grail.
doesn't it? That's the promise of tinyRadar. It's designed as a millimeter wave or millimeter radar-based fitness tracker, specifically engineered to overcome those critical shortcomings we just spent time discussing with wearables and cameras.
So it's using radar waves, basically.
Exactly. Sensing your movements with invisible radio waves.
Okay, let's break down those advantages, though.
Right. First, the brilliance of contactless sensing. Because it uses radar, it doesn't need to be strapped to your body at all,
Instantly solves the comfort and skin irritation issue.
instantly. And it also sidesteps those accuracy issues caused by sweat or the fact that a wearable only sees one part of you. Instead, tinyRadar tracks your whole body motion.
That's key for accuracy, especially for complex exercises.
Absolutely crucial. Far superior to wearables that are stuck on one body part. Second advantage, and this is truly transformative, inherent privacy preservation.
Okay, how does radar do that better than a camera?
Because unlike cameras capturing detailed video or wearables grabbing personal location data, tinyRadar generates something called compact point cloud data.
Point cloud data, so not an image.
Not an image of you at all. Think of it more like a sparse map of reflective points showing movement in 3D space. This data inherently protects user privacy because it collects only activity data AD, remember, like your movements, your rep counts.
But not the personal data or geolocation data.
Exactly. It preserves your anonymity. It doesn't collect PD, your name, age, or GD. It's like it knows what you're doing, but it fundamentally doesn't know who you are or where you are beyond its immediate vicinity.
That's a critical distinction. Activity, not identity.
Precisely. And third, it's incredibly robust. Unlike cameras that struggle in dim light,
Or fog.
right? tinyRadar functions effectively even in pitch black conditions. So whether you're an early bird doing pre-dawn workouts or a night owl, you can exercise whenever suits you without worrying about visibility affecting the tracking.
So contactless, private, robust sounds compelling. And, looking at the broader implications here, tinyRadar really embodies the ideals of edge computing.
Edge computing, meaning the processing happens on the device itself.
Exactly. Processing data right where it's collected, directly on the tinyRadar device. Previous MMA wave radar systems, the research points out, often relied heavily on external PCs for the heavy-duty processing.
Right, we mentioned that. More hardware, more power draw.
Yes, drastically increases power consumption,
Yeah.
severely limits portability, scalability, just makes it less practical for the average person. But tinyRadar is different. The ingenious part is that it implements all the necessary signal processing and the sophisticated AI models directly on the edge.
On the device's own chip.
On its specialized resource-constrained hardware, yes. This approach delivers real-time, fast, portable, and inherently more secure solutions. Sources 5, 20, and 21 really emphasize this benefit.
More secure because the data doesn't have to travel far.
Precisely. Your sensitive fitness data isn't being shipped off to some distant cloud server for analysis. It's processed locally right there in the room with you. That gives you much greater control and peace of mind over your personal information.
That feels like where things should be heading. Privacy first tech.
It's a powerful demonstration of that principle in action.
So what kind of tech actually powers this breakthrough? What's under the hood?
Okay, at its heart is a specific piece of hardware. The Texas Instruments IWR 1843 millimeter wave radar board.
IWR 1843.
Okay, you can think of that as the device's combined eyes and brain. This board then works closely with an ESP32 chip.
Ah, the ESP32, common in IoT devices. What does that do here?
The ESP32 primarily handles the wireless communication, sending those valuable insights, the exercise type and rep counts, to your smartphone over Bluetooth Low Energy, or BLE.
Got it. So the IWR 1843 does the sensing and thinking. The ESP32 does the talking to your phone.
A good way to put it. And the IWR 1843 itself is a pretty powerful component. It operates in the 76 to 81 gigahertz frequency range.
That's quite high frequency. What does that enable?
It allows it to provide incredibly high-resolution point cloud data of the surrounding environment. This high resolution is absolutely key to differentiating between very subtle human activities with impressive precision. It's collecting a huge amount of detail about how things move in its field of view, even small movements.
So it's not just seeing blobs, it's seeing fine detail in motion.
Exactly. But the real ingenuity, I think, lies in the integration of powerful processing units, all tightly packed onto that single IWR 1843 chip.
What kind of units are we talking about?
It features an on-chip hardware accelerator, or HWA. Think of that as a specialized engine for certain heavy calculations. Alongside that, there's a 200 megahertz Cortex-R4F microcontroller, which is like the main coordinator,
Okay.
and a 600 megahertz C674X digital signal processor, or DSP. The DSP is really the workhorse for the complex signal processing algorithms.
Wow, HWA, Cortex-R4F, and a DSP all on one chip.
Yes. This remarkable integration of processing power is what enables tinyRadar to perform those complex operations, the signal processing, the deep learning models, right there on the device itself in real time.
No need to send raw data elsewhere.
Exactly. No need to offload bandwidth-hungry raw radar data to a larger external computer. This compact, self-sufficient processing capability is fundamental to its edge computing advantage. It's really a testament to incredible microchip engineering.
Consolidating what used to need multiple parts into one efficient package.
And directly impacting its portability, power efficiency, and cost.
And this isn't just like a theoretical concept or a lab experiment, right? It's a working system.
Absolutely. The research involved developing a complete end-to-end solution. This meant not just designing the radar sensing and the software algorithms, but also tackling the complex challenge of getting these different hardware components, the IWR 1843 radar chip and the ESP32 communication chip, to talk to each other and cooperate seamlessly.
How do they manage that integration?
They achieved this by integrating them using a separate daughter board, essentially a small circuit board connecting the two, and they meticulously developed the software integration and synchronization routines needed to manage the tasks running on the different processors.
So a lot of careful engineering to make it all work together.
Definitely. The result is a truly complete system, designed for, as they put it, a plug-and-play experience for the end user. It aims to eliminate the need for complex, frustrating setups.
You just set it up, plug it in, and it works.
Yeah.
That's the dream.
That's the goal, yes. Okay, so let's get into the science of how it sees. At its core, tinyRadar uses a technology called frequency-modulated continuous wave radar, or FMCW radar.
FMCW. Okay, break that down.
Imagine it like a highly sophisticated sonar system, but instead of sound waves, it's constantly sending out invisible chirps of radio waves.
Chirps, like bird sounds.
Huh, not quite. These chirps are special signals where the frequency increases linearly, smoothly ramps up over a very short time as they're transmitted. A collection of these chirps sent out together forms what's called a frame.
So constantly sending out these sweeping radio signals, probing the environment.
Exactly. Constantly probing. The radar is very precisely configured with specific parameters for these chirps and frames, optimized for detecting human-scale movement. For instance, the system described uses one transmit antenna, TX, to send out the signals,
Okay.
and 4 receive antennas, RX, to capture the reflections. Using multiple receive antennas significantly helps in gathering more detailed spatial information about your environment and your movements within it. It gives it better vision, essentially.
More ears listening for the echoes. Makes sense.
Yeah.
So how do these invisible chirps actually turn into something useful, like a map of my movements?
That's where the sophisticated signal processing comes in. It's a clever journey, transforming those raw waves into actionable data. First, when those transmitted chirps hit you or anything else in the room and bounce back, they mix with the signals the radar is still transmitting at that moment.
Okay, the outgoing and incoming waves mix.
Yes. This mixing creates what's called an intermediate frequency, or IF, signal. This IF signal is essentially a lower frequency signal, but it still contains all the critical information about range and velocity. It's easier to handle electronically.
Got it. Lower frequency, same info.
Right. This IF signal is then digitized by an onboard analog-to-digital converter, or ADC. That turns the continuous analog wave into discrete digital data points that the processors can actually understand and work with.
Okay, so now it's digital data. What happens next?
From there, the processing chain gets really interesting and efficient. The frequency of that digitized IF signal turns out to be directly related to how far away the target you is from the radar.
The frequency tells you the distance.
Exactly. So a mathematical operation called a fast Fourier transform, or FFT, is performed on this digitized data. This specific operation is called range FFT, and its whole purpose is to extract that range information precisely.
Okay, FFT gives you range.
Yes. And what's truly ingenious here in the tinyRadar system is that this initial range processing step is performed incredibly efficiently by that specialized hardware accelerator, the HWA.
The HWA we mentioned earlier.
Right. And it does this right during the data acquisition phase while it's still collecting the data for the chirp.
Whoa, so it's processing while it's sensing.
Yes. It's a brilliant example of task parallelization. The device simultaneously collects data and begins processing it, which saves valuable time and makes real-time analysis possible. It's like taking a photo and instantly knowing how far away everything in the picture is.
That is seriously efficient. Okay, so that's distance. What about speed? How fast I'm moving?
Good question. To figure out your speed, or velocity, tinyRadar looks at something slightly different. The phase differences in the IF signals from consecutive chirps. Tiny shifts in phase reveal how fast something is moving towards or away from the radar.
Phase shifts equal velocity.
Okay. So another FFT operation, this one called Doppler FFT, is applied. It's applied across multiple chirps within a frame, effectively transforming range time data into what we call range velocity maps.
Range velocity map, so distance and speed combined.
Exactly. But before that Doppler FFT, there's a crucial step: static clutter removal.
Static clutter, you mean like my couch?
Precisely. Your couch, the wall, the bookshelf, the exercise bike sitting in the corner, they're all stationary, but they still reflect radar signals.
Right, they'd show up in the data.
They would. This clever static clutter removal step uses a method described in the source material, essentially averaging signals over time to identify and subtract the signals coming from all those static objects.
So it filters out the furniture.
It filters out the furniture, yes. So the radar can focus purely on moving objects, which in this context is primarily you doing your exercises. This is absolutely essential for accurate fitness tracking.
Makes sense. You don't want it counting your couch doing crunches.
Exactly. It ensures tinyRadar isn't fooled by static objects, focusing only on your dynamic movements. And this critical processing, the static clutter removal and the Doppler FFT, is handled by that powerful 600 MHz C674X digital signal processor, the DSP.
Okay, the DSP does the heavy lifting for speed and filtering.
Right. And this leads to an even deeper insight. To build a truly comprehensive picture of the movement, the range velocity maps generated from the 4 different receiving antennas are carefully combined.
Combining the data from all 4 ears.
Precisely. This involves a process called incoherent addition across the antennas and also across the different range bins distances. This helps to consolidate the information and reduce noise, creating a concise representation called a velocity column for each moment in time, each frame.
A velocity column, a snapshot of velocities.
A snapshot of the velocity profile at that instant. These individual velocity columns are then intelligently stitched together across multiple frames over time to generate the final key output, a velocity time map or VT map.
Ah, the VT map. We mentioned that earlier.
Yes. You can visualize this fascinating progression quite clearly in figures 1D and 3 of the source material, showing how it goes from raw signals to this informative map.
It's amazing how abstract radio waves get turned into something so specific.
It really is. It's a systematic transformation through a series of sophisticated mathematical operations. FFTs, clutter removal, incoherent addition, all performed efficiently on the DSP to reveal precise information about movement. And it culminates in this VT map, which is absolutely crucial for the next stage: activity recognition.
A beautiful example of distilling complex data into something interpretable.
And importantly, something interpretable without ever creating a visual image of you. That's key.
So what does this VT map actually look like to tinyRadar? How does it interpret it?
Well, visually, if you were to plot it like in the paper, it looks a bit like a spectrogram or a heat map. But conceptually, think of it as a unique signature, or almost like a fingerprint of your movement. It shows how your velocity profile changes over the duration of the map, typically a few seconds.
So different exercises create different patterns.
Exactly. Each exercise you perform, a squat, a lunge, jogging, will create a distinct, recognizable pattern in these VT maps based on the speed and direction of your body parts over time. It's a dynamic, time series representation of your motion.
Capturing the essence of the activity.
Precisely. And this VT map is the crucial input that the system then feeds into its AI algorithms to understand what you're doing and how many times you're doing it.
Okay, that makes sense. It's the input for the AI.
Now, a key consideration here is why V2 maps specifically. Why not some other representation?
Yeah, good question.
They seem to be so effective because they capture the inherent periodicity and the complex dynamics of human movement in a way that's rich enough for advanced AI, like a neural network, to understand, but sparse and abstract enough to inherently protect privacy. They encode all the crucial information needed for classifying the exercise type and for accurately counting repetitions without ever needing to visualize your actual body, your face, or any other personal identifiers.
The sweet spot between useful data and privacy.
Exactly. That makes them the ideal input for the onboard classification and repetition counting algorithms. It strikes that perfect balance.
Okay, now for the really juicy bit.
Yeah.
What exercises did they actually teach tinyRadar to recognize?
They trained and tested it on 8 specific distinct exercises. We're talking crossover toe touch,
Okay,
crunches, jogging, lateral squats,
got it.
lunges, hand rotations, squats, and importantly, it also recognizes rest,
Rest meaning just standing still.
or meaning the person is idle or perhaps not even present in the detection zone. It needs to differentiate activity from inactivity.
Right, 8 exercises plus rest. That's a decent starting set.
It is. And what's truly remarkable, as you can see vividly in Figure 2 of the research paper, is that you can literally see the unique visual patterns these different exercises create in the VT maps.
Like visual fingerprints.
Exactly like visual fingerprints. Each map in that figure shows time on the x-axis, typically from 0 to about 4.5 seconds, and velocity on the y-axis, ranging usually from -2 to +2 meters per second, negative for movement towards the radar, positive for away.
And they look different.
Oh, very different. Jogging has a clear alternating pattern, squats have a distinct up and down signature, crunches look different again. The unique visual signatures for each exercise are quite striking, which is what allows the AI to learn to tell them apart so effectively.
Cool. You can almost see the rhythm of the exercise.
You can. Now, regarding the data used to teach it this, the robustness of any AI system fundamentally hinges on the quality and quantity of its training data.
Garbage in, garbage out, right?
Precisely. For tinyRadar, data was meticulously collected from 14 different human subjects.
Okay, 14 people.
And here's a critical detail for ensuring it works in the real world. 10 of these subjects were used exclusively for training the model. Their data taught the AI.
And the other 4?
The remaining 4 were kept entirely separate. Their data was used only for testing the already trained model. This is known as subject-independent testing.
Why is it so important?
It's paramount. It evaluates the system's ability to generalize, to accurately classify movements from people it has never seen or learned from before. It proves it didn't just memorize the training people, but actually learn the underlying patterns of the exercises.
So it should work for new users too.
That's the goal, yes. The setup was consistent. The radar was placed at about 1 meter height, and exercises were performed largely in the line of sight. The training data set itself was quite extensive.
How much data are we talking?
It comprised 400 minutes of exercise data. That translates to approximately 343,000 individual radar frames.
Wow, that's a lot of frames.
It is. And after careful data cleaning and segmenting this raw data into meaningful chunks corresponding to exercises, it resulted in 4,461 distinct VT maps used for training. Each of these maps was a 64 by 64 pixel representation.
4,461 examples for the AI to learn from.
Exactly. This rigorous data collection, the large volume, and especially that strict separation of training and testing data are essential guarantees for assessing tinyRadar's accuracy and reliability across different users and real-world scenarios. All right, let's talk about the AI, the brain. What I find particularly compelling here is their choice of a convolutional neural network, or CNN, for the activity classification task.
CNNs, okay. Those are common in image recognition, right?
Exactly. And that's relevant because VT maps, while not visual images, have that grid-like, pattern-rich structure that CNNs are exceptionally good at analyzing.
Makes sense.
Now, unlike older, more traditional machine learning algorithms that often required manual feature engineering, where humans had to figure out and tell the computer exactly what specific features to look for in the data.
Like, look for this specific peak or this slope.
Precisely. CNNs are different. They are data-driven classification networks. They learn the important features directly from the VT maps during the training process. They autonomously identify the subtle yet distinct patterns that differentiate the exercises.
So it teaches itself what a squat looks like in velocity data.
In essence, yes. The VT maps provide those unique activity signatures, making them perfectly suited for a CNN to process and classify.
Okay, so they trained a CNN. We're talking about putting some serious intelligence directly onto that tiny radar chip, right?
That's the goal of tinyML, tiny machine learning. The proposed CNN architecture, which is detailed in Figure 4 of the research, was trained on those 4,461 VT maps we mentioned.
How long do they train it for?
Over an extensive 5,000 epochs, which means the network saw the entire dataset 5,000 times to refine its understanding. They used state-of-the-art optimization techniques, things like the atom optimizer with L2 regularization, to ensure it learned efficiently and, crucially, generalized well to new unseen data.
Okay, standard deep learning training. But how big is the final model? Can it really fit on a small chip?
That's the truly innovative part. The resulting trained CNN is incredibly compact. It contains only 1,496 parameters.
Only 1,496. That sounds tiny.
It is remarkably small for a neural network. These parameters are the learned weights and biases that define the network's connections. Initially, they are stored in a standard 32-bit format. But even so, the small number of parameters is essential for running on resource-constrained hardware.
But they made it even smaller, right? You mentioned quantization.
Exactly. After this initial offline training, a crucial step called post-training quantization was performed using a tool called the CAFE framework.
Okay, quantization. What does that actually mean for you, the user?
It means taking those 32-bit parameters and compressing them down, in this case, to just 8 bits of information each.
From 32 bits down to 8. That's a big reduction.
It is. It provided a significant four-fold advantage in terms of both memory saving the model takes up much less space and processing speed, because calculations with 8-bit numbers are much faster for the processor.
So the AI model becomes super compact and runs incredibly fast on that tiny chip.
Precisely. It's what makes the whole system practical for real-time use. This quantization step is massive. It's what makes powerful deep learning models feasible on resource-constrained edge devices like tinyRadar.
Balancing accuracy with the limits of the hardware.
Exactly. It strikes that critical balance between accuracy and the computational footprint. So this quantized, lean, 8-bit CNN is then deployed onto the Cortex R4F microcontroller on the radar board.
Using specialized software libraries.
Yes, using optimized libraries called CMSIS NN APIs, which are specifically designed for running neural networks efficiently on ARM Cortex microcontrollers. And as we keep emphasizing, because it's so important, it's critically tested on subjects who were not part of the original training set.
To prove it works for anyone.
To prove its robust, subject-independent accuracy in the real world. Without this kind of optimization, especially the quantization, running sophisticated neural networks directly on tiny hardware like this would simply be impossible. It would keep advanced AI tethered to bigger, power-hungry systems or the cloud.
Okay, so that's how it knows what exercise I'm doing. But what about counting the reps? Let's unpack that. How does it count?
Right, a repetition detective. It's another clever piece of engineering, also running primarily on that DSP C674X processor. It's not just a simple tally counter.
It sees the rhythm somehow.
Exactly. It leverages the fact that the VT map itself shows periodicity related to the repetitions of an exercise. Now, theoretically, you could use something like a 2D fast Fourier transform directly on the VT map to find that dominant frequency, which corresponds to the rep rate.
Fun.
But performing a full 2D FFT is computationally very intensive. It would be far too demanding for the onboard DSP to do in real time alongside everything else.
Too slow, too much power.
Right. So instead, tinyRadar uses a much more efficient approach. It cleverly derives a one-dimensional envelope from the VT maps.
A 1D envelope from a 2D map.
How? Here's the simplified idea. It takes 4 consecutive VT maps, remember. Each is 64 by 64 pixels, and stitches them together side by side into what they call an observation window. That makes a wider map, 64 pixels high by 256 pixels wide, 464.
Okay, a wider snapshot in time.
Yes. It then essentially compresses the rich two-dimensional velocity information within that window down into a single rhythmic line in the envelope. It finds the beat of your repetitions by analyzing the frequency content, specifically the magnitude spectrum of that 1D envelope.
Analyzing a 1D line is much easier than a 2D map.
Much, much more efficient for real-time processing on the DSP. This method allows it to accurately detect the rhythm and periodicity of your exercise, not just classify single snapshots.
Okay, so it turns the map into a line, then finds the beat. Clever.
What I find particularly neat here is the ingenuity in actually deriving these repetition counts reliably. It's not a simple heuristic. It's quite a sophisticated series of signal processing steps, all meticulously implemented on the DSP as outlined back in Figure 5 of the research.
Can you walk us through those steps briefly?
Sure. First, that 64 by 256 observation window is normalized to an 8-bit unsigned format. This just ensures consistent data scaling for the subsequent steps.
Okay, normalization first.
Then, the observation window is intelligently split into positive velocity and negative velocity halves.
Why split it?
This is a subtle but important step designed to mitigate what they call spurious signatures, basically, deceptive patterns in the data that aren't related to the main repetition and could lead to miscalculations. By analyzing both halves and picking the most confident result later, it improves robustness.
Smart. Filter out potential errors early.
Exactly. Following this, a step called binarization is applied. This uses thresholding against the mean value to essentially assign an equal weight or value to all the effective pixels that represent significant movement, helping to generate a smoother, cleaner, one-dimensional envelope later on. It cuts through some of the noise.
Okay, binarization for a cleaner signal.
Then, that crucial 1D envelope is actually generated. This is done by computing the average velocity across each frame, each vertical slice of the binarized observation window. So 256 frames wide gives you a 256-point envelope signal.
Got it. Average velocity over time.
Now, to refine this envelope further and ensure maximum accuracy, a low-pass filtering step is applied. This uses something called an exponentially weighted moving average, or EWMA, filter. Its job is to precisely eliminate high-frequency noise from the envelope signal.
Smooth out the bumps.
Smooth out the irrelevant, fast jitters, yes. This makes the underlying consistent repetition pattern much clearer and easier to detect accurately.
Okay, filtering. What's next?
Next is detrending. This is performed by subtracting the local mean value calculated over a sliding window. The purpose here is to remove any gradual trends or slow shifts in the signal that might occur from you naturally varying your exercise rate slightly, or maybe shifting your position relative to the radar.
So it focuses purely on the repeating pattern, not slow drifts.
Precisely. It makes the core periodicity of your reps even more apparent and stable. Finally, the payoff. A fast Fourier transform, an FFT, is performed on this cleaned-up, detrended 1D envelope.
Another FFT.
Yes, but a much simpler 1D FFT this time. The repetition count, or rather the frequency, is then determined by finding the index corresponding to the maximum peak in the resulting magnitude spectrum. Where the energy is strongest, that's your repetition rate.
Find the strongest beat.
Find the strongest beat. A confidence score, which they call beta, is also computed for this detected peak, indicating how reliable or clear that peak is. The algorithm then intelligently selects the count from either the positive or negative velocity half analyzed earlier that has the maximum confidence score.
Takes the best guess.
Takes the most confident result. These individual repetition counts, calculated over each observation window, are then accumulated over time. And the total actual repetition count for the exercise is computed using a specific formula, equation 18 in the paper, when the system detects that you've changed to a different exercise or stopped.
Wow. That's a lot more complex than just counting 1, 2, 3.
It is. It's a complex yet remarkably efficient process, all running on that DSP, specifically designed to extract a reliable beat from even complex human motion signatures, filtering out noise and variations. It really is like a highly trained signal processing detective picking up the subtle rhythm of your workout. Okay, so we've talked about the theory, the algorithms. How does this all come together in the real world? The real-time hardware implementation of tinyRadar is, frankly, a marvel of integration and synchronization. It's a true symphony of those specialized processors working in perfect harmony.
The HWA, the DSP, the Cortex R4F.
Exactly. It operates by meticulously orchestrating the different tasks running on those different processors. When the board first powers on, everything gets initialized. The RF front end for the radar, the UART communication ports, the ESP32 wireless module, all the necessary drivers.
Standard boot up sequence.
Pretty much. Then, specialized software tasks are created on both the Cortex R4F, which they call the Master Subsystem, or MSS, and the DSP C6704X, the Digital Signal Subsystem, or DSS, to manage the data flow and communications between them. Plus, that specific inference task is created on the Cortex R4F, ready to do the exercise classification.
Okay, tasks are ready. How does it handle the incoming radar data?
So during what's called frame processing, which repeats continuously for every incoming radar frame, the HWA efficiently performs that initial range FFT on the raw chirp data right as it's being acquired. Remember that parallel processing.
Right, sensing and processing range simultaneously.
Exactly. Once the HWA has done its part for a frame, the DSP C674X takes over. It performs the Doppler processing, including static clutter removal, and generates those critical velocity columns we discussed.
Okay, frame by frame.
Frame by frame. These velocity columns are then intelligently stored in something called a ring buffer.
A ring buffer, what's that?
It's a clever memory management technique. Instead of constantly allocating new memory, it overwrites the oldest data once the buffer is full. It keeps memory usage minimal and very efficient, crucial for embedded systems.
Got it, efficient storage.
Now for the classification. After the system has processed the first 64 frames and stored their velocity columns in the ring buffer, the DSP signals the Cortex-R4F. The Cortex-R4F then triggers that inference task to run the CNN and classify the exercise based on those 64 frames, which form the first VT map.
So it waits for enough data to make a map, then classifies.
Right, and this classification process then repeats efficiently. It doesn't wait for another whole 64 frames. Instead, it repeats with every 3 new frames that come in using a sliding window approach over the ring buffer.
Sliding window.
Yeah, it drops the oldest 3 frames and adds the newest 3, then reclassifies. This allows for continuous, near-instantaneous monitoring and quick detection of changes in activity.
So it's constantly updating its guess.
Exactly. When the inference task detects that the exercise label has changed, meaning you've switched exercises, it writes the newly identified exercise label to the user UART port, ready to be sent out.
Okay, so that's classification happening continuously. What about the rep counting?
The repetition counting algorithm, which needs a longer view of the data, kicks in after the first 256 frames have been processed, enough for that 64 by 256 observation window.
Needs more data to find the rhythm.
Right. It calculates the reps for that window, and then it updates its calculation every 16 frames thereafter, again, using a sliding window approach on its input buffer. It continuously accumulates these counts internally.
Accumulating as they go.
Yes. When the system detects that you've changed exercises based on the classifier output, it finalizes the total repetition count for the exercise you just finished using that specific formula mentioned earlier and sends that final count out.
Okay, so it gives you the total when you switch.
Precisely. All this vital information, your detected exercise type, and the final accurate repetition count is then seamlessly sent from the main radar board, specifically the Cortex-R4F, to the ESP32 chip via that UART connection.
And the ESP32 sends it to my phone.
And the ESP32 then wirelessly transmits it to your smartphone application using Bluetooth Low Energy.
So what does this highly synchronized, complex dance of processors and data really mean for me as someone using it?
It means you get instant or very near instant accurate feedback. The tinyRadar is constantly processing your movements behind the scenes, classifying what you're doing, counting your reps, all on the fly, without you ever having to press a button or interact with it directly.
Just automatic tracking.
Automatic, seamless, real-time tracking. It's a smooth flow of data from your movement through the radar processing right to your phone app, giving you immediate, trustworthy insights into your workout without any noticeable lag or delay.
It really does sound like having a hyper-attentive, invisible coach just watching and logging everything perfectly.
That's a great analogy. And this detailed breakdown of the hardware implementation, the task management, the communication between processors, it truly showcases the meticulous engineering required for real edge computing to work effectively in the real world.
It's not simple stuff.
Not at all. The task parallelization, where different specialized processors handle specific parts of the signal processing chain efficiently, combined with things like the ring buffer implementation for data storage, these are absolutely critical design choices for minimizing latency and keeping the memory footprint tiny.
Making it fast and efficient.
Exactly. This integrated, highly optimized approach is what enables tinyRadar to deliver high-performance, real-time results on such a very compact and resource-constrained system. It's what makes it truly practical for a smart home setting without needing a huge power brick or a noisy external computer.
Okay, practicality is key. Now, for the moment of truth we've been building up to, how good is tinyRadar's accuracy? Does it live up to the promise?
Prepare to be impressed. The results reported are really quite remarkable. That 8-bit quantized CNN, the brain recognizing the exercises,
Yeah.
it achieved an outstanding 97% overall subject-independent classification accuracy.
97% across people it never trained on.
Yes. 97% accurate in recognizing the correct exercise, tested rigorously on those 4 new human subjects who were not part of the original training data. That's incredibly high and strongly validates its real-world applicability.
Wow, so it's almost always spot on, even if it's never seen me do a squat before.
That's the implication. Looking deeper at the specifics presented in Table 3 of the paper, some exercises like jogging and lunges were actually classified with a perfect 100% accuracy in their tests.
Perfect. Perfect.
Even the exercise with the lowest reported accuracy, which was crunches, still achieved a very strong 90.6%.
90% is still pretty great for the hardest one.
Absolutely. That's a level of precision you could really trust to accurately categorize your workout routine, even with diverse movements.
Okay, classification accuracy. A plus Z. What about counting the reps? Did it nail that too?
It came incredibly close. tinyRadar delivered an average repetition counting accuracy of 96% across 80 different test cases.
96% average accuracy on reps. That's also fantastic.
It is. In these tests, users performed anywhere between 20 to 120 repetitions of the various exercises, so it was tested over a decent range. That 96% average means you can really trust the numbers you're getting for your sets without needing to keep that mental tally yourself.
Freedom from counting.
Yeah.
Okay, any specific details on rep accuracy? Like, was it better for some exercises?
Yes, looking closer at the box plot they provided, which is Figure 7, you can see the distribution of errors. The maximum median error observed was only a minuscule 2.2%, and that was for crunches, which are perhaps trickier to segment perfectly.
Still, only 2% off on average for the hardest one.
Exactly. And even better, for several exercises, jogging, lateral squats, and squats, the median error reported was 0%.
Zero error, meaning it counted flawlessly.
Meaning, for many common movements in their tests, tinyRadar counted the reps perfectly. Every single time. It just nailed it.
That is seriously impressive. 97% on type, 96% on count.
This naturally leads us to wonder, why is the accuracy so consistently high, especially for the subject-independent testing?
Yeah, what's the secret sauce?
It really speaks to the fundamental robustness of that VT map representation itself. These velocity time maps, because they capture the inherent periodicity and the subtle dynamics of human movement rather than just surface-level visual detailing.
It captured the essence of the movement.
Exactly. They provide a rich yet abstract signature that the CNN can learn incredibly effectively from. This allows the CNN to generalize the patterns of human movement across a wide range of individuals, different body types, slight variations in form, rather than just memorizing how specific training individuals moved.
So it learns the exercise, not the person.
Precisely. And that ability to generalize is the hallmark of a truly reliable, scalable, and practical system that can work well for diverse users right out of the box.
Okay, amazing accuracy. But what about the tiny part of tinyML? How much power and memory does this thing actually use? Is it efficient?
Ah, yes, the resource footprint. This is where the tinyML aspect truly shines, and the numbers are quite compelling. Let's talk memory utilization first.
Okay.
That entire CNN inference engine, the part actually running the classification model, uses only a minuscule 11.36 kilobytes of memory space while it's running.
Only 11 kb, that's nothing?
It's incredibly small. Out of that, just 1.46 KB is for storing the actual model parameters, those 1,496 quantized weights and biases. The rest is temporary space for calculations, the output activations.
So the model itself is tiny.
Extremely tiny. That 11.36 KOB total utilizes a mere 5.76% of the total available data RAM on the device's microcontroller. Plenty of room left over.
Wow. What about the other processing, the velocity columns, the rep counting?
Also very efficient. The velocity column generation chain has a memory footprint of about 560 kb, and the repetition counting chain uses only around 40 kb. These primarily use the L3 RAM, which is a type of high-speed on-chip memory designed for exactly this kind of real-time signal processing on the DSP.
Still sounds pretty contained overall.
Very much so. Now, processing latency, how fast it does things, is also critical. Table 2 in the paper provides a detailed breakdown, but the key takeaway is that each stage is highly optimized for speed to enable that real-time performance.
And the bottom line, power consumption. Is it sipping power or gulping it?
Definitely sipping. The total tinyRadar system power consumption, including the RF front end, which transmits and receives the radar signals, is estimated to be only about 1 watt.
1 watt, that's like less than an old phone charger.
Much less than many modern ones, yes. Breaking it down by component, the Cortex R4F microcontroller consumes about 80 milliwatts. The DSP C670X uses around 350 milliwatts. It's doing the heavy signal processing. And the HWA around 100 milliwatts. And get this. The CNN inference engine itself, the AI part, is incredibly power efficient. It consumes only about 48.64 milliwatts.
Less than 50 milliwatts for the AI.
Yes. And that represents just over 60% of the Cortex R4F's total CPU resources when it's active. These minute memory footprints and the exceptionally low power consumption are precisely what enable true, edge-based, always-on applications.
So what does this all mean? We're talking about a system that's incredibly efficient. It's not a power hog. It's tiny in terms of memory use.
Making it ideal for a smart home setting, where you want devices to be unobtrusive, low power, and potentially always available. This is crucial for sustainable and truly portable health technology that can operate efficiently without being a drain on resources or requiring constant battery changes.
Okay, so if you compare tinyRadar to the competition, wearables, cameras, maybe other radar attempts,
Yeah.
how does it stack up overall?
If you look at the qualitative comparison, like the one presented in Table 4 of the research,
Yeah.
tinyRadar really seems to carve out its own distinct niche, offering a unique combination of advantages. Traditional wearable trackers, as we discussed, provide rich types of information, heart rate, etc., but often with only moderate accuracy for movement, plus those nagging issues of discomfort and privacy.
Right.
Then you have other non-contact technologies. Camera-based systems, or even some earlier millimeter-wave radar solutions, might offer high accuracy in some cases, but often at the steep cost of computational overhead. They frequently require those external PCs for processing, which impacts cost, portability, and power. And cameras, of course, come with those inherent significant privacy concerns.
Okay, so where does tinyRadar fit?
tinyRadar, based on this research, appears to perform better overall by hitting a sweet spot. It offers truly high accuracy, remember, 97% classification, 96% repetition counting, achieved with a remarkably compact onboard classification model running efficiently on the edge.
High accuracy, low resources.
Exactly. Plus, it's robust in low light conditions, unlike cameras. And crucially, its use of sparse point cloud data inherently preserves user privacy in a way cameras simply cannot. It doesn't just try to protect privacy. The data itself is less revealing.
So it's not just another gadget. It feels like a fundamentally different approach that directly addresses the core weaknesses of everything else out there.
That's a great way to put it. It offers a superior balance of accuracy, privacy, efficiency, and practicality for in-home use. It really could change the game.
It seems like it's hitting all the right notes.
This actually brings up an interesting point about the convergence of capabilities we're seeing here. tinyRadar isn't just an incremental improvement over, say, wearables. It represents a significant leap forward because it manages to deliver the kind of high accuracy you might expect from much more complex, often power-hungry, non-contact systems.
Like the PC-connected ones.
Right. But it does so with the efficiency and the robust privacy benefits you'd normally associate with much more constrained, simpler, embedded devices.
Best of both worlds.
It's getting close to that, yes. It's a powerful combination that fundamentally changes the landscape of personal fitness tracking. It moves us towards a future where sophisticated monitoring is both highly effective, widely accessible, and deeply respectful of your personal space and data security.
It's a bold vision for a smarter, more private health tech.
It really is.
Okay, so tinyRadar sounds genuinely amazing, almost too good to be true in some ways. But what can it do yet? Like any groundbreaking tech, especially in its early stages, it must have some current limitations, right? It's important we acknowledge those too.
Absolutely, and the researchers are upfront about this. For instance, the system described in this paper is primarily designed for single-person detection.
Ah, okay. So if my partner and I are working out together in the same room.
Right now, it wouldn't distinguish between you two reliably. It's focused on tracking one individual within its field of view. That's a clear area for future development.
Makes sense. What else?
There's also a practical range limit. It detects activity effectively up to approximately 8 meters, or about 26 feet.
That sounds pretty decent for most rooms, though.
It is, but it also performs best when the person is generally within its direct line of sight. The paper notes that if you deviate too much from that line of sight, or if there are major obstructions, the classification accuracy can decrease.
So you need to be somewhat in front of it, generally speaking.
Generally, yes. And finally, the current implementation they describe is designed as a wall-mounted system. It's intended for personalized spaces, like your home gym, your living room, a specific monitored room.
So not something you carry around with you.
Not this iteration, no. It's a starting point focusing on in-place monitoring. It's definitely not the final frontier, but it's a remarkably strong starting point, laying down a very solid foundation for this type of technology.
Okay, single person, line of sight preferred, wall mounted. Good to know the current boundaries. But what about the future? Where could this go?
The future potential is what's truly fascinating here. It's not just about what tinyRadar is today, but what it could become tomorrow. The proposed architecture itself, as highlighted in the research, has the inherent potential to be scaled significantly. The underlying principles, the way it processes data, could be adapted.
Scaled how?
Well, for one, it could potentially be developed to detect multiple people simultaneously. That's a huge step, opening doors for tracking group fitness classes or monitoring multiple occupants in a household.
Okay, multi-person tracking, that's big.
Huge. And it could also be trained to classify a much broader, more nuanced range of activities beyond the initial 8 exercises. Think yoga poses, physical therapy movements, maybe even daily living activities.
Expanding the dictionary of movements it understands.
Exactly. And this inherent scalability hints at a future where this kind of contactless monitoring could support not just fitness, but also critical healthcare applications.
Like what?
Imagine its potential for robust, reliable fall detection for elderly individuals living alone.
That's a massive area of need.
Massive. It could allow for remote monitoring of patients with conditions like dementia or Alzheimer's,
Yeah.
doing so in a dignified and privacy-preserving manner within their own homes, ensuring their safety without intrusive cameras or the burden of wearables they might forget or refuse to wear.
Wow. That could genuinely improve lives. Safety without sacrificing privacy.
That's the potential. Furthermore, this specific work is significant because it's noted as one of the very first successful demonstrations of using a tiny ML-based CNN implementation directly on these MOM wave radar boards using VT maps for human activity classification and fitness tracking combined.
So it's pioneering this specific approach.
It really is paving the way, demonstrating the feasibility and high performance of this edge AI approach with radar. It opens the door for countless further innovations in this rapidly evolving field of smart health and ambient sensing. It's not just a product, it feels like a platform for future breakthroughs.
So thinking about the bigger picture then, what does this all mean? It feels like this isn't just about counting your squats more accurately anymore.
Not at all.
It feels like a foundational step, doesn't it? A step towards a whole new generation of smart, maybe even invisible tech that can genuinely enhance our well-being.
I think that's right. It's about creating intelligent systems that are deeply integrated into our environment, providing crucial insights and support.
But doing it quietly, respectfully?
Yes, doing so respectfully, efficiently, and with that unparalleled privacy focus, processing data right at the edge where your data truly belongs primarily to you.
It's a really exciting glimpse into maybe a healthier, certainly a more private technological future.
Agreed. A very promising direction. Hashtag tag outro.
So let's recap. We've taken a really deep dive today into tinyRadar, what feels like a truly innovative solution that tackles some of the biggest headaches, the biggest compromises of current fitness tech. We've seen how it's contactless, right? Eliminating that discomfort, the hygiene concerns of wearables.
Plus.
Huge. It inherently protects your privacy by design, only collecting that anonymous activity data, not who you are or where you are. It provides incredibly accurate whole-body tracking, 97% on exercise type, 96% on rep counts in their tests.
Impressive numbers.
And maybe most remarkably, it does all of this on a tiny, super power-efficient chip thanks to the magic of edge computing and tiny machine learning.
It really is a remarkable fusion of advanced radar sensing and groundbreaking efficient AI.
It is.
And this, I think, raises an important question for you, our listener, to ponder. As technology becomes ever more embedded in our daily lives, woven into the fabric of our homes, how do we effectively balance the undeniable convenience it offers with our essential needs for privacy and accuracy?
The core dilemma.
It is. And tinyRadar offers a really compelling blueprint for that future. It demonstrates powerfully that we don't necessarily have to sacrifice one for the other, privacy for functionality or vice versa.
We can have
It shows how thoughtful, intelligent design, focusing on edge processing and inherently private data types, can lead to technology that genuinely empowers you. Empowers you to take control of your well-being without imposing on your personal space or compromising your fundamental security.
That's a future I think we can all get behind.
Yeah.
Now, here's a final thought to leave you with, something building on all this.
Okay.
Imagine a future where your home itself, the environment around you, becomes your most trusted health companion. Silently, respectfully, guiding your well-being, providing those personalized insights into your movements, your activity levels, your fitness progress.
Without needing anything on you?
Without ever needing a sweaty wearable or a watchful camera eye or a data-hungry cloud server constantly collecting your information, just ambient, helpful intelligence.
Mhm.
What kind of positive impact could that future have on our daily health habits, on our motivation, on our peace of mind, and ultimately just on our overall quality of life? Something to think about.